So, thank you for the introduction. Yeah, as you can see, there is no Android in the title. And so we're taking actually a little bit broader perspective here. It's not just like for phones and so on, but it's for embedded devices, especially ones that are based on RISC processors. My name is Matthias Neugschwandtner. Thank you for the introduction. And actually, I did the work together with Colin Moliner, who would have had the slot today, but unfortunately, he couldn't come. Recently started a new job, and most of the work was actually done we did together at Northeastern University. Okay, well, let's get started. As I said, it's a little bit a broader perspective, and I'm going to talk about embedded devices, of which, of course, the phone, not especially the smartphone, but like any phones are just one of them, right? And if you look at embedded devices, they're really interesting because they're produced in very large quantities. They're not actually a computer, but they are a computer in a sense. They are often based on low-cost, RISC-based CPUs and produced in masses. Of course, there are exceptions as well. For example, CPUs for smartphones that have more features. And so still, most of the devices run full-fledged operating systems, sometimes stripped down to certain degrees, some features removed, some features added, and so on. But for example, yeah, if you take a look at, of course, Android is Linux, and many smart TVs actually run Linux, and routers run derivatives of Linux. Why is embedded devices interesting from a security point of view? Because they are very valuable targets. They're always on, they contain interesting personal data, especially phones, right? And sometimes they control quite important things. And of course, they contain software vulnerabilities. So the software runs of them might be subject to memory corruption vulnerabilities, and so they're exploited like desktop and servers. However, the problem with embedded devices in general is that the mitigations on those devices are often, not always, but very often, not state-of-the-art. So, native code, I'm really glad that we've heard native code being mentioned before already. Native code and memory corruption, why do we talk about that? Well, yeah, we've heard Android, of course, the apps run Java, but it's definitely possible to run native code as well, and just in the talk before, we have been introduced to stage fright already. So even on Android, you can have sometimes native code running if developers run a more insecure app. Let's put it that way. If you take a look at state-of-the-art mitigations, the well-known ones, there is data execution prevention, which is really nice because you can make memory pages non-executable, and this definitely hinders code injection. But again, this requires hardware support, which only proper CPUs, so the more higher end, for example, ARM and MIPS devices do have. And emulation exists, but it's usually slow. And they can also be bypassed to some extent using code reuse techniques such as return to library or return-oriented programming. Then there's address-based layered randomization, which is also state-of-the-art. Basically move code to an unpredictable location in memory so that it can't be exploited using code reuse. This again can be bypassed, although it's hard, of course, using information leaks, and so return-oriented programming works again. Then we've already also had control flow integrity being mentioned in the talk before, which basically detects whether code blocks are executed out of order to mitigate code reuse attacks. But in order to work efficiently, it either requires access to source code or compiler support, and in other cases, it leads to really high overhead. Then again, from a very different angle, there's system call or policy enforcement. There are methods like SLinux and app armor or system call anomaly detection, but they require usually a per app configuration or to basically learn what the application is doing. Then again, there was some novel research that uses hardware features that were not originally designed for security, but can be used for this as well to heighten security on devices. For example, the last branch record CPU register that basically tracks the last branches that can be used for to detect code reuse attacks. And there's also performance measurement counters. This can be used for the same reason, but the problem with them again is that they're x86 only usually. They're not present on RISC and lower end devices. Okay, so our idea was, can we somehow leverage common hardware features of RISC for security? There are many RISC flavors, there's ARM, there's MIPS, Super H, and so on, and they all follow same design basically. And at the same time, we wanted to avoid a very specific functionality, to avoid using specific functionalities such as the last branch record of x86. And so when we look at those architecture features, of RISC, there's RISC uses register-only operations, so you have this load-store architecture that you always load from memory into a register and save back from this again. There's a couple of specialized registers, and you have many registers. For example, in control flow, we'll come back to that later. You have fixed instruction length that makes it a little bit more easy to disassemble, whereas you have to variable instruction length on x86. And you usually have enforcement of instruction or address alignment, so that you can't just jump into the middle of an instruction, which you would normally do with return-oriented programming. So our goal was to bring state-of-the-art mitigations to embedded RISC devices. We wanted to build a lightweight exploit mitigation that is also suitable for more budget systems, that uses RISC hardware features, and that's the third feature, that is tailored for binary only or common off-the-shelf programs basically, where you often don't have the source code available. So you're bound to using a certain library, and you only have the library in binary, but not the source code for it. Okay, taking a sidestep, when we look at the fundamentals of exploits, exploits use operating system functionality. So to read or write data or to launch a program, they will, or process, they will usually trap into the kernel and see that they can perform the certain functionality. And one insight is that the operating system usage of an exploit usually differs from that of an original program. So either different system calls are used, or they're used with different parameters. And our idea was that if we can ensure that the runtime operating system usage is coherent with the operating usage, with the OS usage in the binary executable that is stored on the disk, then we would definitely get a security benefit out of that. So we wanted to make sure that system calls that are being used are actually also used by the executable that is stored on the disk, that system call argument matches, and that the call chain that leads up to these system calls, that they also match. And we coined the whole thing binary integrity, or short, bintegrity. From a slightly different angle, if you look at this, so many people that have been in the security field have definitely heard of all the system call monitors and so on, and policy-based solutions where you lock down what an application can do. But the problem with policy-based solutions is that policies, first they need to be defined, and then they need to be kept updated. If you do make them too wide, then maybe an attacker can bypass them. If you make them too narrow, maybe the app doesn't work correctly anymore. If you update the app, you add some more new functionality, you might actually break the app and it doesn't run anymore. So with bintegrity, we have the nice approach that the application binary is actually the policy. So the binary, the program itself, provides us with all the information about what it is doing. And yeah, the idea is that we track the program's runtime state, and we always compare it with a state basically that we extract from the binary image. And if we have non-matching states, so if we see something diverge here, then we can say, okay, an attack has happened. What are the core features of bintegrity? We provide something like dep-like functionality. I don't exactly like to say that we just provide data execution prevention, because it's actually a little bit more that we do. So what we do is we only execute code that is present on the binary on the disk. There is some super lightweight CFI methods that we use. And we also provide basically a system call filter policy approach without actually having to specify a policy. And yeah, works on binaries, there's no rewrite effort needed, there's no instrumentation effort needed, and also no extra configuration. If you take a look at the threat model that we take into account, what we assume is that we have a trusted kernel, so we protect user space code basically. we see, okay, we trust all the binaries that are stored on the disk because, of course, they are basically our ground truth. And we assume that the executables and libraries are not modified by an attacker. However, the memory, so basically the process runtime state is, and the memory that is used is untrusted because we would try to fight off memory corruption attacks. So, an overview of how the system works. If we start out with a binary executable that is stored on a disk and it's been launched, then we end up with a runtime process image that has all the memory and registers and so on associated with it. And at some point, because it wants to do something, the process will issue a system call and request service from the operating system. So that's where we intercept, and we basically check and take a look at the binary executable and at the runtime process and see, okay, has the runtime process been corrupted in any way? Is it not behaving according to the binary on the disk? And if that's okay, we will just let the operating system call proceed. If not, we terminate the program. What kind of information do we extract from the runtime state, or what do we basically need? What we have here is like the typical state of a process at the time of a system call. So you have the program that first performs a function call into a library, say libc, where you usually have some a system call wrapper, and the system call wrapper then actually performs the actual system call into the kernel where the system call is being taken care of by the system call handler. So the information that we have at the system call invocation is first the return address, which points back into the library. And what we also have is the system call number, so we know, of course, which system call has been invoked. And we do have the system call arguments. So basically, okay, say write, okay, which file descriptor do we write to? And then what we have as well on RISC is the link address. A link address is pretty nice because it's the register containing the return address of the last function invocation, which will then point back into the program. And on MIPS, there is actually even one additional register that we can take, that we can use, because the ABI on MIPS specifies that you usually use an extra register to perform indirect jumps, so we have the target for this one as well. Okay, given all that information, we now need to inspect the binary, right? So we need to take a look at the binary on the disk. And here we have a function. We have a function prolog. Say this is the assembly code that is stored on the disk, where we reserve some stack space. We have the argument assignment. Here we can see the arguments which are being loaded into the argument registers. This is also pretty RISC standard. So you pass the arguments to a function invocation via registers. And then we have a function call here via the T9 register, which is the standard register to perform an indirect function call over. And the final, the mop instruction is basically where the link address points back into. So now from this link address offset in the binary, so this is basically the code that's been stored on the disk, right? Because we want to get our ground truth. We start to disassemble backwards, and we do that either until the function beginning or until we hit some control flow diversion. And when we stop disassembling backwards, we start to execute that code snippet basically forward, and then we extract all the invariants, which are the concrete values at the end of the execution. So in this case, we would know, for example, after this execution emulation, that in the argument register A0, we have there needs to be a 7, right? And yeah, as I said, so this is static analysis that we perform on the binary executable on the disk and not on the memory contents. Okay, how can we use this to actually enforce this binary integrity? So there's three basic pillars, let's put it that way. The first of them is code provenance. So we check basically where do the function invocations originate from, and we only allow legit locations. So say if we have a function invocation that comes from a stack or data segment or something, then we then this is, of course, not legit. Then we have code integrity, where we check whether the call chain is reflected by the binary itself, and whether the system call arguments that we can see match the invariants that we have extracted before from the binary on the disk. And the third thing that we do is symbol integrity. Here we check whether the system call wrappers that are, or the system call wrapper that is being used, whether it has actually been imported by the native code program that has been executed. So to enforce this code provenance, which is like our, basically, that's the super data execution prevention that we do. That's why I don't really like the word data execution prevention, because we do more a little bit. So we first construct our trusted application code base, and this trusted application code base basically contains all the valid code regions of the process runtime image. So these are the mapped text segments of the running process itself, and it also includes the text segments of libraries, of course, and it's been fixated after linking stage. So anything, that's outside this trusted application code base is actually invalid. So both the return addresses, the return address of the system call and the link address need to point into those code regions. For enforcing code integrity, again, I have two assembly snippets. As you can see, this talk is a little bit more down to the depths. So what we can check here is on the left-hand side we have the program code basically that has been executed by the program. You can see that mmap should be called here in the libc, for example, and on the right-hand side we have the system call wrapper, which actually then will execute this mmap system code. So knowing the return address, we can check whether the predecessor of the return address actually is a system call. So the return address will point to the mop instruction on the right-hand side, and so this is the first thing that we can verify. Okay, is the code actually there? And then the next thing that we can check is has the right system call been invoked? Because the system call number, of course, is usually being assigned right above the system call invocation. Then the next thing that we can do is check the link address, and we can check whether the predecessor of the link address is really like similar to the system call case, is actually really a jump address, the address where there's an instruction that issues a jump, and whether the target of the branch actually matches the callee, so whether the right system call wrapper has actually been invoked. And what we can also check is whether the actual system call arguments match the invariants that we have extracted before. For symbol integrity, so if you think of just a normal program that uses mmap, then the symbol mmap has to be, on the one hand, exported by the library, which would be libc usually, and it has to be imported by the program, right? So it has to be in the import table of the actual program. And with symbol integrity, what we basically do is we check that the symbol of the function that we have identified by the return address. So in libc, okay, we can see that mmap is being used. So and mmap is associated with the mmap export. We check that it also has been imported by the binary that has been identified by the link address. So if the binary, for example, say system is being used, and system has never been imported by the binary to begin with, by the program, then this is also clearly not a valid invocation. So which kind of attacks can we mitigate with these techniques? So first of all, there's basic code injection attacks. So say I want to inject code into the data segment, then the defense would be code provenance, because it's in a data segment and there's say, I don't know, I put something in the heap and it's not actually in the binary on the disk. Yeah, we have code provenance that will prevent this from happening. If I decide, okay, so say the heap is being protected, so I try to overwrite the text segment. Say I mark the text segment writable, then again, we have code integrity because the instructions will actually mismatch with the binary on the disk. For code reuse attacks, it's getting a little bit more complicated. So there's an indirect jump gadget being used, then we will see that the target of the branch actually does not match, Or another way would be that the symbol integrity doesn't, symbol integrity basically fires. So that, for example, say system has not been imported. And if you use return-oriented programming, so code reuse attack again, and you actually use a gadget that calls a library function instead directly without going through an indirect jump gadget, then we can still check if we have static arguments, whether those arguments match. So whether the runtime arguments actually match from the arguments that we have extracted from the binary running on the disk. I've also, since this is, since we just had this table before, I've got some concrete examples. So what we have here is such an indirect jump gadget, as I said before. So you usually write it PLT, this address is being loaded into T9, and then the argument is being loaded into A0, and then we have the indirect jump via T9. So in this case, if an attacker would abuse this by putting something else in T9 and then just going directly to this indirect jump, then T9 would not match the invariant, and we would basically detect that. Here we have here we have a fixed jump gadget. This is that directly branches to write, so to the write system call wrapper. And as we can see here, it statically sets the argument 0 to 1, which basically corresponds to standard out. So for example, this gadget could not be reused to write to a different file descriptor. Here's a similar case actually with mmap. That happens actually quite often. So in this case, we have, for example, here that mmap is originally being called with an argument to make the parsed memory region just read an executable, which is the value 5. And again, if an attacker would say modify this here and to load 7, which would correspond to read-write executable rights into the argument register and try to overwrite this, we would again see that we got an argument mismatch here. And this is actually the case that I mentioned before. So say I've got an indirect jump gadget that does not have any restrictions. So the last thing that can still kick in here is that if T9 has been replaced by the address of the system function in libc, but system is not used by the program itself, so it's not in the import table, then we would again see okay, it has not been imported by the program, so we terminate it. And if you take a look at the typical ROP stager for return-oriented programming, which is basically a combination of normal return-oriented program and traditional shell code, that first uses return-oriented programming to mark an executable memory region, mark a memory region executable, sorry, and basically put more payload in there. And then on MIPS would also need to flush the cache to basically manifest that in the memory. Then here the code reuse mitigation would kick in, and at the same time, when it starts to try to execute the traditional shell code, the payload in this memory region, we would have the code injection mitigation. So we implemented this whole system as a kernel module, the integrity kernel module for Linux, and which basically consists of a couple of parts. So it interacts with both the process to extract the runtime information and with the binaries on the disk. Then we have the emulation engine, which consists of an ELF parser, because we need to parse the binaries on the disk, and actually that also works with strip binaries, so this is not a problem. It has a disassembler and a complete code emulator in it that we implemented for both ARM and the MIPS architecture. And we also have an invariant cache, which I will come back to later, because these are quite costly operations, all this disassembling and emulation, so we also cache some information. Our implementation supports different checking levels because not all functions are critical the same way, and so we can reduce checking to increase performance in some ways. So this is an option that that this module supports. So we have basically level 1 checks that just check for code provenance. We have level 2 checks that include on top of that code integrity, and we have level 3 checks that on top of that includes symbol integrity as well. So basically the full program. And yeah, so in Linux we identified 33 security critical system calls, and we instrument basically 11 at checking level 2 and 22 at checking level 3. The reason for this is also that some functions are just used by every program, so checking them to, for example, for symbol integrity does not provide any additional security benefit. For example, if you, write will probably be used by almost every program. So we just check for code integrity here. Yeah, of course, we also did a performance evaluation. We added something to the kernel, right? So there's got to be some overhead. And what we did is we used a Buffalo router that runs Linux, so OpenBRT. And we used Apache Benchmark and Nginx, and we got an approximate runtime overhead of 2% on this stuff. And we also evaluated on a Galaxy Nexus phone with just running stock Android, although I don't remember the exact Android version that we ran. We used the N22 benchmark because it was the best that we could find, and measured the Android runtime and the I/O subsystem. And here we had an even lower runtime overhead. We also did an internal performance evaluation. As I said before, we have quite costly operations that are involved. We read and parse files that are stored on a disk on a system call invocation, so that usually takes lots of time. We also have this instruction emulation. And we also have a certain memory footprint. So we have the kernel module code, which is not that big. And we also have the invariant cache. The invariant cache actually stores these invariants, so this, the data that we extract from the binaries for around 257 code points. So this roughly requires a total of 12 kilobytes per process. So again, it's not that much. This graph actually shows how much caching, how vital caching is to the whole thing. So basically the red bars shows how much the overhead would be, and this is on a log scale, if we would not have caching, but as soon as the caching for the code points kicks in, our overhead is significantly lower. So whenever we have a cache hit, it's actually, it's not that bad. And here we have, so what we did here is we had the web server running on the router, and we browsed that web page on that router web server with a browser running on Android on ARM. And what we can see here nicely is that at program startup, we have lots of invariant extractions. So there's, of course, lots of system calls have been done at program startup. Then caching kicks in, and we are basically idling regarding to invariant extractions. And only as soon as we actually surf to the website and open it up, we have again a peak, and then any subsequent accesses basically don't exercise super new code paths, so it kind of levels out over the time. Okay, coming to conclusions. So what we did is we used architectural features of RISC that are basically intrinsic to RISC and that are fairly generic to improve the security of embedded devices. And we provide so this is of additional benefit for platforms without hardware security. This will not be of super additional benefit for, I don't know, top of the line Android phones that already run Android, the newest version, but will definitely benefit lower end budget devices. And we provide DAP-like functionality for those devices. We have lightweight CFI for binary only in applications, so we don't require source code. And a system called filter policy extraction method from the actual binary image, so you don't need to write extra policies for this. And it also has pretty low overhead and is transparent to applications. This is also not research vaporware. This stuff actually exists, and if you're interested, you can also have a look at the source code here. So, yeah. Thank you for the talk. Attention.
Thanks for that. Any questions right now?
So my question is, you said that your solution is different from previous works because you don't need kind of policy, you can just look into the binary. So my question is why you think it is much different, because to resolve possible targets, you have to analyze control flow graph of the application, and maybe previous works, they just extracted the policy, then stored it somewhere. You don't store it, you just do it on the fly. Why conceptually do you think it is different?
Well, so one thing that I think is different is that that basically everything happens at runtime, so it's transparent. There's no policy that a user has to take care of or anything being involved.
Usually these solutions would not involve the user, they would just analyze the binary, they would make a policy in an automated way and then enforce it at runtime. What you are doing, you do the same, but just you don't store it, you just apply it immediately. And I doubt that you can really extract very precise policies, because actually static analysis cannot resolve the targets very precisely, so your policy would be loose. This is my guess.
Yeah, so this is also a pretty lightweight solution, right? We do this at runtime and we do it as system call invocation. And we also, we don't extract the whole CFG of the program. We don't do that. So really what we just do is at runtime, when the system call happens, we peek back into the binary and we look what kind of code is there and what does this code do. So there's no complete CFG generation involved. We just take a look at those two code points. It's really targeted at the very low level right before the system call invocation.
So you would probably be able to prohibit some, for sure, malicious transfers, but you don't know, so you still allow code transfers, many targets, and you cannot be sure if the one which happens currently is the correct one.
I'm not sure I understand it entirely. So, but no, it's not a pure CFI solution that will enforce the whole path up to the system call.
Yeah, I mean, because can you ensure that by verifying the binary, you can resolve the exact target?
So.
By static analysis of your binary, can you be sure that...
No, you can. I mean, you can never be sure just using
that's
static analysis.
That's what my point is. So
yes.
You can never be sure, and it doesn't matter if you do lightweight.
No, it's also not a. It's not a prevention mechanism. It's a mitigation.
Okay.
It will not help against all attacks, and if you have a very super determined attacker, he will for sure find a way of crafting a path that will try to bypass it.
Okay, thank you.
But it's definitely, I mean, it's with many security solutions, it's another way of raising the bar, right?
Okay, thank you.
So first of all, I think this is a very interesting solution. Maybe I just got lost in the details, but exploits love to execute functions like system, and what about the target application actually uses system, so the import is legit and the arguments are not invariant. Can your solution mitigate the risk?
So that completely depends on how system is invoked and how it is being used, right? So if a system is always being used with a string constant that is stored in the binary, then yes, because we have the string constant in the binary. If I write native code, then it invokes system with a dynamically generated string. I'm not sure it's like super security sensitive coding. And then, yeah. I mean, it's in some way, of course, limited to what the application gives you. Everything that we can enforce depends on how it has been written originally.
Okay, I'm afraid most calls to system actually do like construct the argument dynamically. Thank you.
Hi. You mentioned that you're actually comparing the binary that loaded into the kernel against the binary allocated on the file system. Am I correct?
Yeah, we are comparing the runtime process image in memory against the binary that is stored on the disk.
Okay. So actually in Android, in Java application, the binary on the disk is in DEX format or something that the Dalvik is actually jitting, and you receive something totally different from what located on the disk. Am I right?
Yes, so this applies to native code level. It does not apply to Java or JITted code. I mean, we are compatible with JIT,
Yeah.
because basically what we do is we vet the JIT layer, right?
Yeah.
But not the Java code that has been executed.
Okay. Thank you.
Yes, hi. So first of all, good job. I really like the work. But I was wondering whether you could also port this towards the x86 platform. So as you mentioned, there are already solutions there, but they don't focus on ARM. But do you think that your solution
So porting it
could be-
to x86, is that, did I
Sorry?
understand it correctly?
Yeah, so whether or not you can port Bintegrity to the x86 platform.
So there are certain difficulties involved on x86 because, for example, we use heavily backwards disassembly, which is easy on RISC because we have fixed instruction set length. On CISC, this is, I mean, yeah, you never really know what you're going to backwards disassemble, right? So this would definitely be one of the struggles. And then what we also, so we rely heavily on the register-based architecture. So basically that passes arguments in registers, usually tries not to modify them in a certain way, and so on, which you don't have to this extent on x86. I mean, I know on 64-bit that usually the calling convention is to pass already the arguments in registers, but yes, that would only target then 64 bits.
Thank you.
Any other questions at the moment? It falls to me to have a tough one again. Did you try it with a specific exploit?
Did we try with a specific exploit? The problem is no, we did not, which does sound bad at the beginning, right? But we took a look at various exploits, but they are very hard to recreate because you need, for example, we looked at router exploits, but you need to have the exact same router model running the exact same software on that router, and we struggled to get the whole setup basically running because some of the router models are not available anymore. Then you need to go to eBay, and I thought, okay, I can spend the time better than doing this. But we looked at the actual exploits and how they work, and yes, actually, I mean, there's a paper under submission to an academic conference that lists several exploits which would have been mitigated using this.
How many of them would still go through?
How many of them would still go through? That would, I don't have exact numbers in my head, so yeah.
Then, thanks again. Thanks a lot.